Purity check complete, specs are nominal.
Digital is built on a foundation of sand, but only the purest electronic-grade silicon can serve as the starting point for modern microchips. Inside crucibles heated to over 1400 degrees Celsius, the raw polysilicon is melted down into a flawless, glowing liquid pool. Using a single seed crystal, the liquid is slowly drawn upward, meticulously freezing atom by atom into a massive, perfect single crystal ingot. To survive the rigorous manufacturing journey ahead, the rough-cut wafers are ground perfectly flat, and their delicate edges are meticulously smoothed. Chemical mechanic polishing transforms the dull gray silicon into a flawless, mirror-like surface, so perfectly flat that variations are measured in single atoms. Before they can become computer chips, the silicon wafers must be subjected to ultra-pure chemical baths, washing away even a single stray atom of dust. The fabrication floor is thousands of times cleaner than an operating room, requiring technicians to be completely sealed away to prevent human contamination. Inside the fab, automated overhead tracks rush sealed pods of wafers between hundreds of specialized processing machines in a delicate, perfectly choreographed dance. Exposed to extreme heat and ultra-pure oxygen, a microscopic layer of protective glass is grown across the wafer, the foundational insulator for billions of transistors. Using extreme ultraviolet light and the flattest mirrors ever created, the intricate blueprint of a processor is photographically printed onto the light-sensitive silicon. A chemical bath dissolves the exposed areas, leaving behind a nanoscale stencil, a physical map of the billions of pathways where electricity will soon flow. Bombarded by glowing, highly reactive plasma gas, microscopic canyons are carved deep into the unprotected areas of the silicon foundation. With the trenches successfully carved, the temporary photorested stencil is burned away and washed clean, leaving behind the permanent architecture of the chip. Acting like a nanoscopic particle accelerator, ion imprinters shoot specific impunity atoms directly into the silicon crystal, fundamentally changing how it conducts electricity. A blinding fraction of a second flash of extreme heat heals the battered silicon lattice, locking the new atoms perfectly into place. Chemical vapor deposition introduces reactive gases that build up solid, microscopically precise layers of insulation over the newly formed transistors. Because a skyscraper cannot be built on an uneven foundation, the wafer is polished perfectly flat again, preparing it for the metal wiring that will connect the transistors. Inside a high-vacuum chamber, a microstorm of pure copper atoms rains down, coating the microscopic trenches with an ultra-thin metallic seed layer. Submerged in an electrified chemical bath, solid copper rapidly grows onto the seed layer, filling the trenches to form the microscopic wiring of the chip. This complex symphony of printing, etching, and plating is repeated dozens of times, building a three-dimensional metropolis of copper highways layer by layer.
A final protective seal is applied over the delicate circuitry, and microscopic solder bumps are grown to act as the chip's electrical bridges to the outside world.
Thousands of microscopic needles touch down on each individual chip, running exhaustive electrical diagnostics to ensure millions of logic gates are functioning perfectly. Defective chips are digitally mapped for disposal, while the entire wafer is ground down to a fraction of a millimeter to allow the final processor to shed heat efficiently. Guided by the digital test map, robotic arms pluck only the perfectly functioning chips from the tape, leaving the defective ones behind. The delicate silicon die must be connected to a robust base. Green substrate boards are prepped with chemical flux to ensure a perfect electrical bond. Flipped upside down, the processor is married to its substrate, perfectly aligning thousands of microscopic solder bumps with the connecting pads below. Traveling through a thermal oven, the microscopic solder bumps melt and fuse, forging thousands of permanent electric bridges between the brain and its body, the underfused station. Liquid epoxy is drawn underneath the silicon by capital action, filling the microscopic gaps to protect the fragile solder joints from physical stress and temperature expansion. A silver metallic lid is sealed over the delicate silicon, providing crucial physical protection and drawing intense heat away from the processor during heavy operation. Now fully assembled, each processor undergoes rigorous optical and X-ray examinations to verify that its internal structure remains completely flawless. Pushed to their absolute limits in high-temperature burn-in ovens, the chips endure hours of intense simulated workloads to guarantee years of reliable operation. Processors are sorted by their maximum stable speeds, and robotic lasers permanently etch their identity and performance ratings directly onto the metal casing. The completed electronic brains are meticulously organized into anti-static trays or wound onto continuous reels, safeguarding them against static electricity and physical shock. Vacuum sealed inside protective moisture barrier bags with desiccant packs, the processors are completely shielded from atmospheric humidity and static discharge during transit. Boxed and extensively barcoded for global tracking, thousands of finished processors are consolidated onto pallets, completing their months-long journey of manufacturing. From a handful of purified sand to the beating heart of our digital world, these microchips now depart to power the innovations of tomorrow.